It's a great pleasure to be here in India. I have some of the most fondest memories of my youth when I actually spent lots of time here in India, and it always struck me that there's such an amazing positive attitude, and I see that this has not really changed. So it's always an incredible pleasure to be back here in India. So this workshop is about anomalies, generalized symmetries, about trying to understand new types of order in many body physics. And so what I would like to do in these lectures is to give a bit of a background and an overview of how you deal with this when you're on the lattice. How can you understand anomalies on the lattice? How can you understand symmetry breaking on the lattice? And especially, what kind of symmetry do you break if you're in one of these exotic topological phases? Because that's not obvious at all, that there is a symmetry that is broken. And I think this is like one of these reasons that so many people are interested in these generalized symmetries, and is that these are symmetries that go beyond the normal Landau paradigm. They go beyond the normal group theoretic flavor, because the symmetries that are broken in topological phases turn out to be much more rich than just normal group type symmetries. Okay, so these can be symmetries that cannot be described by groups. They are symmetries that have to be described by something more general, some more general associative structure. These are like fusion categories. And these are exactly the tools that you need to understand how to describe these systems, but also to simulate them. Okay, so the focus of my lectures will be to explain all these symmetries and ways symmetries are represented, and ways wave functions are represented, and entangled wave functions are represented, and topological wave functions are represented in terms of tensor networks. And it turns out that this is a very natural representation for all these interesting phases, actually for any phase. It doesn't even matter whether it's topological or not, because these tensor networks actually give you the representation theory of these fusion categories. So this is really the way you have to interpret this. So the talks, like the lectures of, there will be quite some overlap actually with the lectures of Julien, although that will not be immediately clear. But what we do is actually try to do the representation theory of these fusion categories, such that you can actually realize this on a lattice. So how do you actually construct lattice models? But what are the symmetries, and what are the symmetries that are broken? So this is actually a work that that goes back a long time. So the workhorse of what we do is called matrix product operators. So this is what this MPO stands for, matrix product operator. This will become clear what it means. But the first works, actually there's an earlier paper where we realized it, but this is basically the first paper where we talk about generalized symmetries in a very consistent sense, in the sense that we construct the representation theory of fusion categories in terms of matrix product operator algebras that can be realized on tensor product spaces. Okay, so this is basically a very general framework for understanding generalized symmetries. And this was 10 years ago. Then 5 years ago, there was actually some other work that we did with mathematicians, Jürgen Fuchs and Christoph Schweigert. And the main person there was actually my PhD student was Lorenz Lotens. So we realized that actually this whole framework can be generalized to something that's called bimodule categories. Okay, it turns out that bimodule categories are exactly the tools needed to understand generalized symmetries, at least for 1D quantum spin systems or 2D topological field theories that are non-chiral. It turns out that bimodule categories are very natural and can be represented very easily using these matrix product operators. And the key was actually collaborating with mathematicians that had developed this very abstract framework of bimodule categories in the context of conformal field theory. There's many other papers, but somehow every 5 years, somehow I produce a paper for every 5 years. Just last month, I posted some lecture notes that were written also with my students some lectures last summer that I gave exactly about these topics in Les Houches. Although these lectures are a bit more general, they encompass also kind of a broader viewpoint on tensor networks. Because what is these tensor networks? These tensor networks seem to give you a very nice theoretical understanding of all these interesting phases or symmetries or anomalies, but they also give you a very powerful numerical framework for dealing with this. Okay? Because you actually are able to do this on the lattice, you're able to write down wave functions with these symmetries, and you can use these wave functions as variational wave functions. And it turns out that the state-of-the-art methods for simulating strongly correlated systems are really based on these tensor networks. So you can use all these tensor networks as a variational method. And maybe some people have heard about DMRG, the density matrix normalization group, is this very special case of one of these tensor network methods. So I will not really touch up onto this unless there's more questions about it. But nevertheless, I want to say some, and maybe in 2 minutes, I want to explain a bit the philosophy of why these tensor networks are so powerful as a computational tool. Okay, so these tensor networks actually they model the entanglement degrees of freedom in your system. So instead of basically writing down a wave function of a many-body system that, of course, has exponentially many components, you basically write down how the different components of your system, the different subsystems, are connected with each other. And that allows you to get a holographic picture of the full wave function, but this holographic picture is in one-to-one correspondence with the full wave function. So you can really kind of use this to calculate any observable, and this allows you to break down this exponential wall. So what you get is basically effectively a manifold of wave functions with very few parameters that captures the low energy physics of all these strongly correlated systems. And this manifold has an extremely interesting structure. Turns out that, like for in the 1D case, it's a Kähler manifold. So it has a complex structure, it has a symplectic structure. So what you can do is effectively project your full physics on that manifold, and then you get some effective theory with Poisson brackets, just some classical equations, and you can just optimize there, and you can really kind of just simulate everything that you want. Yes?
In the description of that sort, you have a notion of semi-classical limits. So what plays the role of the Planck's constant there in such description?
Yeah, it is. So, but it's so you have to think about this as a generalization of Hartree-Fock.
Yeah.
Okay, in Hartree-Fock, you also have like a very low dimensional manifold.
Yes.
That lives in the full many-body wave functions, but it's just you only look at the product states. But it still forms a manifold, and then you can do the physics on the manifold of Slater determinants, and that's how Hartree-Fock works, time-dependent Hartree-Fock. Okay. And that's basically how you understand 90% of all the physics in the world. Okay, by Hartree-Fock. But this is about how do we deal with this in the so there's no real notion of an H bar. The H bar is just there for the equations of motion. But clearly all the things like the Heisenberg principle, this is in there, no? Because these wave functions are embedded in a bigger wave function. So it's a manifold in a much larger wave and a much larger Hilbert space. No, but Hartree-Fock is used in chemistry. No, there's NS finite. Okay, there's. No, but okay, but here there's no real kind of so there's no limit like that, because actually the variational parameters is something that you really can deal with extensive wave functions. You can even work in a thermodynamic limit actually using. But this is not the focus of this lecture. What I want to explain. So there's these two sides of these tensor networks. On the one hand, they give you very powerful numerical methods. On the other hand, they give you a very nice and natural framework for understanding symmetries in topological phases of matter, because they give you representations of these symmetries. Okay? So this is, so as we're all physicists, most of us, I guess, if I think about group theory, I think about representations of groups. I don't think about the abstract notion of a group. Okay? The abstract notion is much harder. And that's, I think, one of the main difficulties certainly that I had when I started looking at these category theories, is that this is a very abstract. It's like the group part. What you want is a representation of it. And once you have a representation, everything is much clearer. Because if you think about SU2, you don't have to think about this very complex geometrical whatever. No, you just think about 2x2 matrices that are half determinant one. Okay, and that's very clear. You can see this in the vector space. And this is exactly what these tensor networks do, actually. These tensor networks will give you they build the representation of these fusion categories on Hilbert spaces. Okay, and this is what I'd like to do. But before starting this, let's briefly repeat something that is just to put things in context. Why we also, for example, why we certainly need to understand what this representation is, because so let's think about the classical Landau paradigm. Okay, the Landau paradigm, it tells you that if you have a certain system, well, actually the Landau paradigm, I only learned this recently by reading some old papers. It dates back to Curie. So actually these French people were the first ones to realize that the key in understanding phases of matter are symmetries. So Pierre Curie, actually not Marie Curie, Pierre Curie, wrote a paper in the end of the 19th century where he very clearly said that if we want to understand phases of matter, we have to understand group theory. Okay? And we have to understand how symmetries are broken. Okay? That the interesting stuff is when symmetries are broken. And this is, of course, the essence of what we call nowadays the Landau paradigm. That phases of matter are characterized by how symmetries are broken. Okay? So more specifically, I have something like Hamiltonian, and it commutes with, let's take some representation of a group. This commutes with these unitary transformations that represent the group. And so this U of G, so I have a group G, and then effectively the different phases of matter can be obtained by looking at subgroups of G. And the subgroups are effectively the subgroups that are not broken. Okay, so if you have a Hamiltonian that commutes with G, then obviously, well, all eigenstates of this Hamiltonian can be arranged into kind of irrep labels, can be labeled by irrep labels of this group. But and if the ground state is unique, then obviously it must have the symmetry. That's very easy that all the eigenspaces of a Hamiltonian that commutes with a unitary transformation must have the symmetry of that Hamiltonian. So if the ground state of your Hamiltonian is unique, it must have the symmetry of your system. But if the ground state is not unique, there's no reason why this ground state should have the symmetry. The only thing that it tells you is that these symmetries kind of will kind of transform all the different ground states into each other. And this is exactly why we need to understand very explicitly what are these unitaries. Because we need to understand these unitaries to understand how to connect all the different ground states to each other. Because you get one ground state, to find the other ones, you have to act with your unity. And of course, the prime example of this is the Ising model. No? So the Ising model, but of course you can go much more general thing. So let's take, as an Ising model, let's take U of G, a tensor product of x's. X. Okay, so this is a representation of the group Z2, because this, so these are sigma x operators. So obviously this, well, of the unitary version at least, and this squares to the identity. So this forms a representation of Z2. And then you say, okay, this is the symmetry. I want to write down Hamiltonians that commute with this symmetry. So simplest one that you can write down is sum over I, Zi plus 1 plus lambda times xi for a spin chain, but it doesn't really matter. You can do this in higher dimensions. You can add higher terms. It doesn't really matter. Then you look at this Hamiltonian, and indeed you see that there's two phases. There's one phase in which the ground state is unique, and of course must have the symmetry. And there's one phase in which the ground state is not unique, where it's symmetry broken. And indeed, the symmetry broken state is when lambda is very small, and there's two ground states, one with all spins up, and one with all spins down in the limit when lambda becomes equal to 0. And indeed, you see that if you act with sigma x on this state, you get that state. Okay, so this is, of course, the very simplistic way in which you can. Okay, but anyway, so you see that group theory and the representations of the group are very important here. Okay, so to understand the whole thing, you need to understand how are these symmetries represented. And actually, the lecture today, I will focus on that particular question. How do you actually represent symmetries on a tensor product space? Because, yes? Yes, no, this is the quantum Ising, of course. This is the this is the Ising model in transverse magnetic field, because you have Z operators and X operators here. No, sorry. So what I will in these lectures, I will focus on the quantum part, but of course, because of the path integral formulation, this is completely equivalent to the classical picture. Okay, so if you do quantum physics in 1D, effectively this is equivalent to statistical physics in 2D. So every argument that I give is valid. So the way you have to transform this, instead of Hamiltonians, you have to work with transfer matrices. Okay, so it's really about symmetries of the transfer matrix of your partition function there. That's effectively the analog. So everything I say actually has a counterpart in statistical physics. And that's okay, so but anyway, so how many ground states? The first question you should ask, if I have a certain group and I break my group to a certain subgroup, that subgroup is the one that is remaining, how many ground states do I have? Okay, that's a very simple question. Well, the ground state is the number of cosets in your theory. Okay, so the number of cosets in your theory will be the number of different ground states in the system when you break your subgroup. And so we want to understand these kind of things, but for much more general, much more interesting symmetries. Okay, so we want to understand this, what happens when you do this for gauge theories? What happens when you do this for generalized symmetries? Okay, what are these symmetries do not form a group, but form a fusion category? And why, again, do we need this? Okay, so the whole point of view of this Landau paradigm, so there's something like a new generalized paradigm. Landau paradigm that tells you that it's not enough to look at groups to understand topological phases of matter. It turns out that there are phases that are not, well, that there's phases that are not adiabatic connected to other phases, but nevertheless they have, basically they keep the same subgroup H. And these are, for example, for 1D systems, these are topological phases. In higher dimensions, there's even very, very different kind of things. So for example, the ideas or the lectures of Julien, he focused a lot on topological order in 2D. He looked at things like the toric code or string nets, or anything that has a categorical symmetry. And what he kind of calculated very explicitly is, if I put a theory on a torus, what is the ground state degeneracy? So obviously, if you have a system with a ground state degeneracy, it must be that the symmetry is broken. Yeah, that's the whole point. Okay, if you have like a ground state degeneracy, it must mean that there is some symmetry somewhere in the system that allows you to map one state to the other one. Okay, and there must be. That's the only way in which you can have an exact eigenvalue. So there's no accidental. Let's say there's no accidental degeneracies in a spectrum. If a spectrum is degenerate, then it must come from a symmetry. And that's exactly the question that we would like to ask. If you have something like a topological phase, what are the symmetries in the system that are broken? And how can I represent these symmetries such that they map one ground state to another one? And it turns out that these symmetries needed for describing these more general topological phases, they are not described anymore by a group, but they are described by something like a fusion category. Okay, so fusion category is effectively generalizing a group. Okay, so it's still something that has objects, like a group. If you have a group, it has simple elements. Okay, so simple elements G. Okay, these are the simple elements of your group, or just the group element G, and you multiply them. Okay, so we have some rules. I have Gi times Gj, that is equal to G, well, I times J. Okay, so this is the whole point of a group. If there's a group multiplication. So fusion category is very simple. So what is the defining property of a group? That's actually the only property that really matters, is that it's associative. Okay, so the associativity of a group is an extremely non-trivial property of a group. So if you write down a Cayley table at random, it will typically not be associative. Okay, so the fact that that all groups can be classified and that you can actually do this whole program is really bound to the fact that there's like an amazing amount of conditions needed such that this group multiplication rule is associative. And that's, of course, also the reason that you can represent groups by matrices. So the representation theory of groups is completely bound on the fact that this is an associative algebra. And turns out that these fusion categories that we deal with have very similar elements. They have simple objects, let's say A, B, and so further. And what we want is fusion rules. So this is nothing more than multiplication of these group elements, N, A, B, C times C, the sum over C. So this is the difference now. What you get is that if I multiply two elements with each other, I cannot just get one outcome, but I can get several outcomes. And of course, there's other kind of conditions in a group that there's like only one unity, there's only one unit element, and this is also kind of the case. So these are integers. Sorry, this is important, isn't it? These are integers. Okay, so because it's like, in this particular case, these are just permutation matrices. It tells you if I know I and j, that's unique k. But the only difference with the, so it turns out that this is not the most general associative structure that makes sense in the context of physics. Okay, so this is, so people have always focused on groups because it turns out that Wigner had said that this is the only thing that matters. But that's exactly why people are excited about topological ordered systems. It turns out that there's more general type of symmetries that matter and that make sense. And these symmetries are described by fusion categories, but in many ways, this is not so much more complicated than group theory, as I will tell you, as you will see. It's very, so what we want to do is now just do the representation theory of these groups. So like I said, like you have a Z2, I have a group, how do I represent them? Well, one representation is, for example, this is the regular representation of Z2, the X. Okay, this gives you the regular representation, and that with this, I can construct models. Okay, so what we want to do is exactly the analog. I have a certain fusion category, and I want to understand how do I construct now the representation theory of this fusion category. So I want to have objects analog to this, okay, that live on a tensor product Hilbert space. Okay, somehow that multiply according to the fusion rules of my algebra. Okay, so, and it turned out that this representation theory of these fusion categories is something that indeed can be realized in terms of matrix product operators. And that's why these matrix product operators play such a central role in the whole discussion of trying to understand and simulating topological order. So what are these matrix product operators? Well, now if you look at this, this is something like, I can represent this as in a tensor network language, this X, well, this is the X operator. It's an X, this is like this. No? So this is the X operator. And I just have a tensor product of X's. And it's obvious that, let's call this, well, this OX. And if I multiply this with itself, okay, so this is nothing more, these two legs are nothing more saying that this is a matrix. This is the matrix X, the left index, the right index of X. And combining two indices is just multiplying, summing over this index. X here. And obviously this thing, OX times OX, is equal to the identity operator. So you see, I construct a representation of my group on a tensor product space. And that's exactly what we want to do now for general fusion categories. But for general fusion categories, turns out that this is much more interesting and much more, from a mathematical point of view, a little bit more intriguing. So it turns out that to represent non-trivial fusion categories, you need another index. You need another index in this direction. So this is an index. And it turns out that this is non-zero. Okay, so this is, for example, let's call this OA. And all these, what I have here now is not a matrix anymore, but a tensor. Okay, so this is a tensor with 4 legs. And I want, let's assume that we have periodic boundary conditions. Actually, at the end of this lecture, if I have time, I will talk about much more general type of boundary conditions. And this turns out that the most general type of boundary conditions can be labeled using something else called tube algebras, for the people that have heard about this. So these tube algebras are nothing more than the boundary conditions, the twisted boundary conditions that you can define for all these different MPOs. But anyway, so I will write down an MPO. So this is an operator that acts on a tensor product Hilbert space. Okay? But of course, it turns out that it's not defined on the full Hilbert space. It's only non-zero on a certain subset. And that's exactly needed because somehow it turns out that that the quantum dimension will be the effective dimension on which this has support. Okay, so this MPO will not have support on the full Hilbert space, but only on the Hilbert space that is represented by somehow this quantum dimension that Julian talked about. But let's do that later, actually. What I have is an MPO. Okay, so this is something that I have tensors here, and if I combine these, so this is nothing more than something like A, I, J, alpha, beta. Okay, this is alpha, beta, I, J. Okay, so it's a tensor with 4 indices, and I combine this, and if I combine this link, it means I have to sum over this index. Yes? Yeah, indeed, that's the whole problem. How do you find representations of this fusion category? So how do you define, how do you obtain all the possible representations? Okay, so this is because it's clear that we need to find all representations, okay? But that's clearly very important in physics to understand all the EREPs. Okay, so we want to find all possible MPO representations of a fusion algebra. And that's exactly the problem that somehow we solved. So I have an OA, I have an OB, and I want this to be a sum over C times OC. Okay, so that's the, yes?
As a projector times a unitary projector onto the image where it acts non-trivially? And
no, not. I don't think that's generally. It's a general. Well, yes, yeah, actually, yes, but again, it's the same study. Okay, I will not really touch on it. If you want to write this as an unitary, this was actually the discussion that we had in a previous talk. You have to take into account all possible boundary conditions. And if you deal with all possible boundary conditions, then actually you can turn this into unitary times a projector. Okay, so this is the whole point about also about dualities and all these kind of things. If you take all the possible topological sectors into account, you actually can see that all these objects become unitaries. So indeed, they are unitaries on some kind of subspaces. That will turn out. But what you see is that these symmetries are much more interesting than normal group-like symmetries in the sense that because there is a connection here, when I act with my symmetry on this side, it's connected, it's correlated, it's entangled with my action here. It's not just acting here and independent there and so further. No, there is actually some entanglement. Okay, so this non-trivial MPOs, this fact that they have a non-trivial bond dimension, and makes sure that the action is entangled. Okay, there's a very non-trivial action. The way you need to represent these symmetries is by using effectively entanglement. So this is a non-trivial quantum circuit. So you can implement all these things indeed as a quantum circuit if you take into account all possible boundary conditions. And then somehow, this quantum circuit has a certain depth, while this depth is just 1. No, it is, no. Okay, okay, so good that you asked me because this is the most important point. What I want is that this algebra, okay, so this is the sum, this is the sum over C and A, B, C. I want, of course, that these structure constants do not depend on the system size. Okay, so this MPO should form a representation of that object independent of how many legs I have. Okay, so it should be a topological thing. Okay, symmetry is something topological. There's no correlation length, there's no length scale involved in this. So this algebra should be completely independent of the system size.
Trees and fusion trees have definitely a 1D nature. That is, you start with.
No, but it's not.
So I was wondering whether your
horizontal axis. It's not a fusion tree.
Is it like the time in the fusion, the depth in the fusion tree?
No, well, but let's come back to this later. But it's not. You should not think about this as a fusion. It's not.
Yeah. Don't you think there has to be some form of connection?
No, but I will explain where fusion trees come into play. But it's not as you think.
Oh, excuse me. What kind of boundary conditions you want?
For the moment, I just do periodic boundary conditions. Periodic.
So
But we will be able to do all possible boundary conditions, and actually all possible boundary conditions are needed to understand the full picture, obviously. And especially also, so the second lecture, I will also talk about dualities. Okay, and what you will see is that dualities and these boundary conditions are extremely important in dualities, because the dualities will actually mix all these different boundary conditions with each other.
Okay, but now it's periodic.
We do periodic because I don't want to make it cool, because actually the boundary conditions are very subtle.
Yeah,
boundary conditions, well, this is completely understood, and turns out that boundary conditions have to be described in terms of tube algebras. But before I can introduce tube algebras, I have to say some more. I have to. Yes. No. So what I want is, given an NABC. And actually, there's more information. But anyway, I have this NABC. It will turn out that this NABC will be able to solve some pentagon equations, to relate some pentagon equations with this. Using this pentagon equation, I will be able to write down explicitly MPOs that have this. And this kind of the number of objects will determine all the bond dimensions. But of course, there's many different representations. No? Like if I give you a group, there's more than one representation. Okay? I want to find all representations. And all these representations will turn out to be. You will be able to obtain them by thinking in terms of bimodule categories. Okay, but again, for me, I'm not a mathematician, I'm a physicist. I understand bimodule categories because I understand their representations. Okay, so for me, this is a much simpler way of dealing with this. Because if you try to read the literature on bimodule categories, it's really hard. But if you know about tensor networks, it's very simple.
Bond dimension like lower bounded by the quantum dimension of this object?
But quantum dimensions are not even integers, no? So what would that mean? No, but okay, we will explicitly construct them. I will construct all of them, and then, but there's obviously some notion that well, there is, yeah. Okay, but let's do some examples. Okay, so let's not following what I to do, but anyway, maybe just to sketch what will happen. So we have these MPOs. These MPOs are the symmetries. Okay, so what is the most important? Probably one of the most useful things that Wigner did is derive the Wigner-Ecker theorem. He says, if I have a Hamiltonian with a certain symmetry, then I can immediately write down all possible Hamiltonians that have that symmetry in terms of the Clebsch-Gordon coefficients. Okay, so that's the first thing that we should do also here. I have now these MPOs. What is the analog of the Wigner-Ecker theorem? What are all the possible Hamiltonians that commute with this? Yeah, and that will turn out to be very simple. So actually, there's once you understand group theory and representation of groups, it will turn out that actually with minor modifications, you will be able to solve all these issues. Okay? And this way, you will be able to find Hamiltonians that commute with this. But it will turn out that actually you can also find tensor networks that represent all possible string nets on the hand of these Clebsch-Gordon coefficients. So these Clebsch-Gordon coefficients will also allow you to build string nets. And these are all these topological string nets, quantum doubles, twisted quantum doubles. They all kind of fit in that framework. Okay, so they will nothing be more than these tensors that commute with these MPOs will allow you to build a whole wealth of wave functions that actually have these symmetries. And this will be the trick to understand basically topological order in a non-chiral phase completely. But it will also allow you to understand actually the topological phases in 1D systems. Yeah, because if you have these 1D systems, it will turn out that these symmetries will be symmetries of somehow these 2D systems, but these 2D systems can have edge modes. Yeah, quantum spin chains with these MPO symmetries will kind of emerge naturally as the edge modes of 2D TFTs. And that's how you kind of map then a TFT to spin chains that might be critical, and that's how you start kind of understanding that you will have a connection between TFTs and CFTs. Okay, so it will turn out that these are the symmetries, CFTs. And indeed, this is not at all surprising, because the first time in physics where these fusion categories appeared was exactly in the context of CFTs. Okay, this was exactly Moore and Zyberg who realized that actually the defect lines in a CFT satisfy, or basically form a fusion category. Turns out that these MPOs that I'm talking about here will be the defect lines in the StatMech descriptions of critical systems. Okay, so all the defect lines that you write down in a StatMech model will be in one-to-one correspondence with these ones. That's why the fusion rules of these objects are, of course, the way defects in CFTs will fuse with each other, because it's just the fusion rules of these symmetries. So it's all about symmetries. It's all about trying to understand this. And indeed, so once you have this and once you understand the representation theory, you can start playing lots of games. And it turns out that there's a whole community, like Upworth is one of doing some very interesting program called SymTFT. Guys, we can reinterpret actually this whole SymTFT in this language. Or maybe I think it's rather different, I think. But the SymTFT people reinterpret this language in terms of field theory, but and string theory, but in some sense it's really the same thing. So there's clearly, once you understand the symmetries, there's a very natural way of connecting topological features to conformal and critical systems. And I hope that I somehow will be able to explain all of this in the next lecture. But what is more? Yes. 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 Exactly. All of these things go through. So it's so what we're doing is really the representation here. So you see, this is something. So you need, this NPOs form the natural. So the only thing you have to do if you think about groups, well, just add some line there. That's it. And then all the things like characters and all, it all goes through. Yes. Yes. Exactly, subalgebras, yes. Yes, of course, yes. Yes, all of these things happen. So a group is just a special case of a fusion category. Yeah, indeed. Yes. Yes. Yeah, because we just do it. We have an explicit construction. So all of these things are very constructive. And at the end, what is nice is that you can just put it in the computer. Okay, so I give you fusion category and you solve the pentagon equation. You need, what you will need is actually the skeletal data of, so to find all possible MPO representations, what you will need is the skeletal data of a bimodule category. Okay, but that turns out that there's not, so Julien talked about one pentagon equations, there's actually 5 pentagon equations that are all connected with each other for these cases. But it's very similar, and actually numerically it's not so complicated to actually find solutions of that. Yes? No, actually, for the moment I don't require this, and actually this all goes through for non-unitary. So it turns out that you can also do this for non-unitary cases. So this NPO algebra still go through. So of course the unitary ones are a special case. Actually, one important thing, because maybe this is confusing, when Julien talked about categories, this unitary modular fusion categories, this will be related to this fusion category in the sense that he talks about the Drinfeld center of that fusion category. Okay, so the fusion categories that Julien talked about are the ones that will emerge out of the systems that have these symmetries. Okay, so the symmetries actually form a much smaller fusion category than the anions that are in that theory. Okay, so like, just to give you an idea, if you want to do the toric code, okay, you would have to start just from this. Okay, so this turns out that the fusion category defined by these symmetries will allow you to construct the toric code. Okay, so it just has a Z2, but obviously there's the center of this Z2 actually has 4 objects, and these are the 4 anions in the toric code. Okay, so it's a bit, could be confusing. So when we talk about these fusion categories, they don't have to be modular whatsoever. They don't have to be braided, because it's the input category, it's the symmetries. what will come out of the theory, if you kind of at the end construct something like a string net using these symmetries, the anions in this theory will automatically kind of form a unitary modular fusion category. Because these are somehow just the excitations in this theory. Okay, so that's that. I hope that this does not more confuse than it does, but in some sense, we are talking about symmetries here. Julien was not talking about symmetries, Julien was talking about the elementary, somehow the topological sectors in the theory. It turns out that actually the Drinfeld center, exactly that Julien talks about, will be in one-to-one correspondence with the boundary conditions. Okay, it will turn out that if you kind of put boundary conditions here, it will turn out to something like this. The possible boundary conditions will be in correspondence with the center. This will be indeed this center of your fusion.
Just a short comment, Frank. I agree with what you're saying, but it rather works the other way around, in the sense that among all UMTCs that I discussed today, some of them are Drinfeld centers, some are not. So we can obviously build a Drinfeld center for an arbitrary UFC, okay? But there are also UMTCs.
No, but I was clear that I said these are the non-chiral ones.
Yeah, okay.
Okay, so this I'm not claiming that I can construct, that I understand the symmetries. So I think this is an extremely interesting open research question. What are the symmetries of the non-chiral whatever, string nets, or not string nets, but topological theories? This is, I'm describing here, it turns out that these are the symmetries of all the string nets, the doubles, twisted quantum doubles, all these kind of things. And if you want to understand the symmetries, you have to understand this. And actually, but not just this, also the edge modes of these theories. And that's exactly where all the CFTs come into play. Okay, so it turns out that there's these describe both the symmetries of 1D quantum spin systems, but also of topological phases of matter. No, it acts on a whole Hilbert space, on a tensor product Hilbert space. No, but this is your Hilbert. This is the Hilbert space on which you're acting. Think about the Ising model. Your Ising model is defined on a tensor product Hilbert space, and the Hilbert space is effectively the same. But MPSs don't play any role here. I'm trying to represent fusion categories using some operators acting on a Hilbert space. And I want this to be happening independent of the system size. Yeah, sure. Just like, yeah, sure, because I will define my, say, you would have an Ising model, you define it indeed, like Z here. Yes, that's spatial. You write down the nearest neighbor. No, okay. This is explicitly a one-dimensional MPO. So it's a one-dimensional spin chain representation. It will act on a spin chain. You can do the same thing in higher dimensions, and we are doing this. But for this, you need a generalization of this. Okay, for what you need for this is actually something that's called P-poles. Okay, so let me draw it. Then this. This we see now. This is the plane. So these objects are these ones. And now you need tensors actually with 6 legs. And these are now the symmetries that basically map from there to there. And now you see that this would happen in 2 dimensions. We can do this, of course, for any lattice. This is called a P-pole. And these are the most general ways in which you can represent 2 categories. Okay, but of course, I don't want to talk about this. But it is of course, there is explicitly something like a 1D. Yes. What do you mean? No, wait. This is acting on a Hilbert space of a dimension that is exponentially large. Okay, so again, if you took a look at the quantum Ising model, okay, this is happening on a Hilbert space that is a tensor product structure. So the Hilbert space has an exponential dimension. Okay, so I have a spin here and a spin there and a spin there. Obviously, the tensor product, well, I know my quantum system, it's something that grows exponentially large. And you want to understand how to represent these symmetries on these tensor product on this tensor product Hilbert spaces. Okay, so let's so to warm up, actually, let's yes. Yeah, I will explain. I will do this. So let's indeed do. Let's actually kind of look at this in a little bit more specific way. Okay, so let's. So we want to represent these things on Hilbert space. So let's actually look at the general group case. Okay, so I have my I have a certain group G, and I have a representation U of G. Let's maybe take the regular representation. It doesn't really matter what. And I take indeed the tensor product of this times this, tensor this, and so further. Okay, so what is the first thing that you have to basically do is to see that indeed, if I have a certain representation U of G, obviously I should decompose this in its irreducible components. Okay, so I should try to find. So if you look at this as a box, this is this box. This is this. So of course, obviously, I should work in a basis in which this is block diagonal. Okay, so that's something that will be important here. Okay, so also in this particular case, we will want to work. We want to kind of label the different invariant subspaces. And the different invariant subspaces in this case are, of course, the IREP labels. Okay, so that means that every one of these things will have a certain label mu that is invariant. And these are the IREP labels of my group. Okay, so these are all the different ways in which I can represent a certain group. Okay, so there's some kind of a label that tells you what is the IREP. And of course, for this given IREP, there's a certain dimension associated to that IREP. And that means that this is the dimension of that matrix. So I have this extra label nu, and for a given nu, put this nu here, I have a certain dimension of a matrix. So it's really very simple, but of course, like if you would take SU2, I could take half integer representation, I could take a spin 1/2 representation, I could take a spin 1 representation. All of these things are allowed. It will turn out that I'm interested in finding all representations. Of course, I have to kind of allow for all possible IREPs. And I could even envision systems in which I have both spin 1/2 and spin 1 systems. Well, I will have to keep all these different objects together. It's basically, these are direct sums of all these different. I can even have a spin 1/2 here and a spin 1 there. So I have to be able to label these things like I want. Okay, so actually, to do this from the point of view of bimodules is already pretty non-trivial. Okay, so basically, if I want to do this, well, let me immediately. So I will write something now that probably doesn't make sense to any of you, except if you are an expert in, or you know about bimodal categories, but it's just to warm you up where we want to go to. So what is the description of this in terms of a bimodule? It will turn out that my input category C is vec of G. So the simple objects of my category, so I have this fusion category, the simple objects are given by the group elements. That's what it means. C is vec of G. It means that the simple objects of my category are just the group elements. This particular case, I will have a vector space, okay, because I'm acting on a vector space. And I will have something like a bimodule, some dual with category D. And this category will be equal to the representation theory of G. So how do I know this? Because these are these labels in this direction. So the labels in this direction that somehow are invariant are these labels nu. So these are these labels nu, or the IREP labels of my category. So from the point of view of somehow abstract category, group theory is about representations of groups. It's actually about bimodules. And what is it? Why is it called a bimodule? Because I'm acting with C on a vector space. So if I act with my group element, I have a certain group element, I act with it. So I act with, so C has an action on M and gives an other element M. But in this particular case, M is just a vector space, so it's just always the same thing. It doesn't do anything. This is nothing. So M only has one element. When we write down M as vec, it means only has one element. It does nothing. So C acts on M, but it just gives back M. M acts on D, and this gives you somehow, let's call this big label nu, that is an element of D. This will turn out that it gives me times. So this is already pretty non-obvious. So if I act with my representation, okay, my labels of my irrep on my vector space, I get a number of, I get a vector space where I basically have to act in a Hilbert space that has a dimension and is equal to the dimension of the irrep of that thing. But again, this is probably complicating things because I have not explained at all what a bimodule is. But this is basically how you will have to interpret it, the normal group theory in terms of bimodules. It will have somehow, I have a module, I act from the left on it with my elements in C, but I can also act on the right of it with my elements in D. And when I act with this, I get several times. So what I get here is new fusion rules because I get new objects. I get object C, I get object in D, I get objects in M, and I will get new fusion rules that tell me how to combine elements of C with M. And it will turn out that these pentagon equations that are these pentagon equations will be the consistency equations that tell you how to kind of construct all these things. Yes? Because it's a module, you're acting, M is both a left module with respect to C and a right module with respect to D. Because it will be that there's fusion rules, okay? So you will get no new fusion rules. This kind, you will get kind of new fusion trees. That's how it works, yes? Well, we will certainly restrict to those, although it turns out, okay, that's an important point again. MPO algebras are more rich than this. Okay, we have constructed actually in recent papers MPO algebras that are not corresponding to semi-simple bimodules, but actually are related to just bi-algebras. Okay, so it turns out that actually they're a bit more general than what we can do, but they are certainly good enough to represent any semi-simple whatever. Okay, but anyway, so you see, this is of course complete overkill. No? So what I'm doing here is complete overkill. But what is already very important in this connection is that you see I have an MPO in this direction. This MPO has bond dimension 1. But I can also construct an MPO now in this direction. But this bond dimension is 1 everywhere. It doesn't really matter because I take the same MPO, but now so this is, now I multiply them like this. Okay, so or maybe I should not draw these indices at all because they are not there, obviously, for this very simple case of a group. Okay, so let's now actually take this group. That's how you actually should have explained this. This is why, of course, this formula fusion got taken. These are these group elements. So I can construct new MPO. So if I have an MPO in this direction, it turns out that to be consistent, I can also construct a different MPO by just taking exactly the same tensors, but instead of connecting these indices, connecting these indices. So I can look at what happens if I multiply MPOs like this. Yeah, so, but there's both space in some sense, but okay, you can think about this. It doesn't really matter. It's just another MPO. Okay, of course, in practice, what we'll do is there will be also lines like this. But now you can see, oh, if I multiply these two, okay, this is an MPO, let's say, with label mu. This is a label mu. Obviously, we all know that we can write this as a direct sum over. This will be n mu nu gamma gamma. I I know that if I take the tensor product of a certain E-rep with the tensor product with another E-rep, that I can decompose this as a direct sum of other E-reps. Okay, that's nothing more how E-reps fuse. Okay, like if I have a spin 1/2 and a spin 1/2, I can write this down as a spin 0 plus a spin 1. And this is exactly this why we call this right-hand side rep of G. With the fusion rules, this will give rise to another category. And this category has fusion rules equal to the E-rep labels or the E-reps of your group. Well, this is again, I'm actually, let's even leave them open, but it doesn't really matter. So they're, in this particular case, indeed, you could say, oh, this doesn't seem to make much sense. Let's actually take them as open boundary conditions. Okay, and actually, this is now happening in terms of open boundary conditions. Okay, because indeed, if you close them, it's just a scalar. Yes, no, let's actually now not close. No, let's just leave this open. This starts somewhere and this ends somewhere. Yes, exactly. Just cut out the vertical line and you see that actually there's a new fusion rules emerging there in this connection. So I can interpret this. So of course, what happens is that in this particular case is that you have your E-rep, you have another E-rep, and there is a Clebsch-Gordon coefficient for which this is equal to this. Okay, so basically there's an object that you pull through that converts these two into another E-rep. So if this is spin 1/2 and this is a spin 1/2, this would be either a 0 or a 1. And that's how you basically see that there's indeed new fusion rules that emerge that are equivalent related to the representation category of your group. And that's another fusion category that also has pentagon equations and all these kind of things. That's why both C and D turn out to be two different categories. But they are very much related to each other. Related because they are a bimodule. And actually, in terms of mathematics, it turns out that these two categories are effectively equivalent. They are Morita equivalent. So what it means is actually, it turns out that, just to connect with what Julian was saying about yesterday, it turns out that the Drinfeld center of C is equal to the Drinfeld center of D. Yes? But again, in some sense, so that has nothing to do with MPOs, what I'm doing here. No? What I'm doing is just rephrasing normal group theory in terms of bimodules. Well, both. Both, that's the thing. The thing is, if I represent these MPOs, it turns out that if this forms an algebra that is consistent, it will turn out that also these will form consistent algebras. And they will kind of give rise to a different category, which is the Morita dual of the original category. Yeah, sure. You can think about this, yes. Yeah, no, but at the end, it will be completely. It doesn't matter whether your Hilbert space will be defined here or there or whatever. So this is indeed, from the point of view of this picture, this is the Hilbert space. Okay, actually, M and D together form the Hilbert space. Okay, but let's actually do something. Okay, so this is complete overkill. No? So I'm just doing normal group theory in this very complicated language.
Frank, what if you don't start from a big G category, but for a more general one? You claim that with this construction, you'll be always
indeed
obtaining another D?
Yes.
So you construct all bimodules?
Exactly. This is what comes out. So we will be able to construct using this. You start with a certain C. The invariant subspaces that will emerge on this level. So the invariant subspaces on this, like I said, the invariant subspaces are labeled by nu. They will form the labels of another category. This category will be represented by these MPOs and will also have a fusion category and will be completely consistent and will give rise to the dual. And that's a completely general picture. And this will happen for any bimodule. Okay, so any bimodule will have an NPO representation. Yes. Yeah, but again, yeah, but yes. No, but these of course have to be the same thing. Okay, this all has, if this is spin 1/2, it has to be spin 1/2 everywhere. Okay, but this is the invariant subspace. This the label. This label has to be the same label everywhere. But again, it's a bit, it's very artificial what I'm doing here, no? Because I don't even have a word. But of course, once you start putting these things, it's much more interesting. But at the end, this is the complete picture. Okay, any bimodule category will be represented as an MPO both in this direction, will have boundaries, and using these symmetries, you will be able to construct basically any string net, any quantum double, any twisted quantum double. Yes. Yeah, well, imagine that they are neighboring, yes, but yes, because we are just fusing, these two ERAPs now. So we know that this is this an ERAP 1/2 and a 1/2. I know that there's a Clebsch-Gordan coefficient that will map that one to a spin 0 or to a spin 1. You get the direct sum here. Yes? Yeah, well, okay, let me give an example. Because let's actually do a gauge theory instead. Okay, so we considered here just a normal spin system, but let's actually now consider how symmetries would act when I have a gauge theory. Okay, so basically, I have my Hilbert space consists out of gauge fields and matter fields. Okay, so I'm drawing it like this, but I will change the picture. But okay, just these are the, let's say these are the matter fields, and these are the gauge fields. And let's actually again take C equal to vec of G. Okay, so actually let's play the game that Benoit was playing yesterday. Okay, we have some kind of, I want to construct certain gauge theory. So I want to have, these are matter fields, these are gauge fields. And if you have a vec G symmetry, then of course, in your gauge theory, your Hilbert space must be such that you satisfy Gauss law everywhere. Okay, so and let's take the convention that all these labels, both the matter and the gauge fields, are just labels in vec of G. You can do this. And the matter fields, and I want it to be such that if this is label G and this is label H, then K has to be such that this is G times H. So that means that if I take any triple A, B, C, then A times B times C minus 1 is equal to 1. That's the Gauss constraint. You have a local Gauss constraint, and this is effectively my group multiplication. Okay, so you turn your global symmetry into a local symmetry. The local symmetry, of course, it's a very trivial case, but you will see how we will get completely different NPO representations if we cannot do this. Okay, so I take something like matter fields, gauge fields. Of course, these matter fields are completely determined by the gauge fields. If I know this gauge field, I know that gauge field, I know exactly what this thing is, because this times this must be equal to this. Okay, so in some sense, these matter fields are completely frozen. They're completely determined by the gauge fields. But nevertheless, I can do this. Okay, I can write down a gauge theory that lives on that Hilbert space and has matter and gauge fields, and I have a Gauss law everywhere. So everywhere, I have this Gauss law satisfied. Okay, but still, this system will have a global symmetry. Okay, actually, and this is something that turns out for one of the other strange reason. For me, it's obvious because we have been working on this for more than 10 years. But what I want to do is not to write all my gauge fields like this. What I want to do is I have my matter fields. I want to write my gauge fields. I want to basically copy my gauge fields. I want somehow to, how do I best kind of do this, but I want to split this gauge field. I want to split this gauge field into copies. Okay, so there's nothing more than if this is label A, then this is also A and A. Yeah, and it turns out that this will be important. Okay, this will be important to kind of come up with the most general construction. But there's nothing fancy about this. If I have, instead of this representation, I will map this to another Hilbert space in which every label A is mapped to an AA. Okay, so if I have, this is my Hilbert space, of course satisfying gauge Gauss laws, and whenever I have a spin A here, I will just write it as AA. And this will be my Hilbert space. And then the reason that I want to do this is that my Gauss law is now local. So I have a local Gauss law. Now I can just look locally whether this thing is satisfied. You know, somehow this becomes my local Hilbert space now. Okay, so I have this gauge theory, I have this field, and now you can ask, what are the symmetries? Are there still global symmetries in the system? So this is, so what are the global symmetries if this is my my Hilbert space? Well, it will turn out that you will be able to write this down, and now you will need an MPO. You will not be able to do this without a certain dimension. With an MPO that looks like this. Here, and so further. So, and again, the fact that this index is doubled is nothing more that if this is an A, this is an A. It's just telling me I just take a copy of my Hilbert space. Okay, so there's nothing fancy about it. It's just that if this label in my Hilbert space is A, then this one is also A. Okay, so let's define. So both this, and this, of course, now are just elements in my group. But again, somehow the Hilbert space is such that if I multiply this with this, it has to be this. There's some non-trivial constraints. Okay, this is the Gauss constraint. The Gauss constraint gives me some non-trivial fusion rules. And this, you already start seeing why I'm doing this. No? So what we will have is basically some M, some D, some other M. I will act with D on M and I get another element in M. I will get a fusion rule. In this particular case, it's particularly simple because it's just groups, but this will be the general kind of picture. Okay, so these are constraints. So in some sense, I can completely even forget about this middle label because it's determined by the two other ones, but let's just keep it. Okay, because I don't mind keeping it because it's just some redundant label. If I know this label and this label, I know this one, but let's just keep it anyway. That is how these MPOs work. So let's see what is the symmetry of this system. Okay, what you see is this is G, this is H, and this is G times H. Okay, so let's actually make this thing, well, this is just diagonal. So let's say if this is label X, and this is still X, let's not change that label. Let's actually define an MPO like this. But let's define the MPO, let's say O of G, such that if this is A, let's call it O of A. If this is G, then this is A times G. Okay, so there's some constraint that if this label is G, then this label has to be A of G. And if this label is H, then this label is A times H. And it's the same for all these objects. And what you can see is that this is now an MPO because it has a non-trivial bond image because this is connected. This is basically, this label is the same as this one. And this label is the same as this one, but these two labels don't have to be equal to each other. If I act with this thing on this, it will change all these labels. Okay, it will kind of multiply all these labels with A. We'll put an A here and an A there and so forth, but will not change the middle labels. And these will turn out to be the symmetries that I'm interested in. Okay, these are the symmetries, the global symmetries that are still there in my gauge theory. Okay, the global symmetries, and this is, of course, exactly what you expect. Okay, so these are the domain wall. If you think about Ising model, these would be the domain wall labels, but they are kind of completely arbitrary. I can start with a 0, I can start with a 1. That's exactly what this operator does. It exchanges the reference state. It tells you if I started somehow with the domain where I call this a 0, then, and let's flip this 1, well, I have to flip them everywhere. And that's exactly what this NPO does. Okay, so this is another way of representing a symmetry. Okay, so this is, now we have a new NPO. So now we have a genuine NPO symmetry for the same. Okay, so these dotted lines. And so further. And if this is A, and I multiply with, and of course you have to contract these loops and all this, and I contract this with a B, then this is obviously nothing more than the NPO A times B. Okay, because indeed the only rule is that if this is G, this is A times G, then I have to, sorry, this is B times A. Okay, so this forms another representation of your group. And again, I have to apologize, in some sense it's completely trivial, but you see it's already a different representation. And this is a representation that has a non-trivial bond dimension, because this label is the same as this one. Okay, so this is entangled. Yeah, so I have 3 legs. Exactly, but of course you have to be so effective. So this could be any element G. Let's say this is element A, and this is G times A. So the effective Hilbert space is just the local Hilbert space is the dimension of your group squared. Okay, because they are not all 3 independent, no? So if I know this one and this one, but that's also not fair because of course this label is the same as this label. Okay, so there's lots of redundancy in this description, but it's needed to come up with somehow the right NPO language. No, this is about symmetries again. I'm not talking about wave functions. I'm talking about operators acting on a Hilbert space. And this will be the symmetries. Yes? Well, okay, exactly. So now we don't have a tensor product Hilbert space anymore because there's some constraints. For example, that this label is equal to this label. Okay, that's a constraint. And that this times this must be equal to this. So this is a constrained Hilbert space. And this will turn out to be the fusion. Of course, we already recognize where we want to, these 3 things will have to fuse to the identity. That's where this kind of thing will come from. Okay, so this is how you will be able to generalize this to general fusion categories. Okay, anyway, what is interesting now, let's try to represent this now in terms of bimodules. This was actually a much harder bimodule than this one. What is the bimodule related to this one? It will turn out that the C is vec of G, M is vec of G, D is vec of G. That is the bimodule that corresponds to this thing. Why is this? Because obviously, what are the invariant subspaces in this direction? They are labeled by the group elements. Okay, because they don't do anything. This NPO is just diagonal in this element. Okay, so the invariant subspaces in this, if I now would construct an NPO in this direction, are labeled just by exactly the same elements as my group. Okay, so the bimodule that I will get in this particular case that I realize with this NPO is exactly this bimodule. And this is always consistent bimodule. And indeed, you see now, if I turn this over this, it's exactly the same object. There's nothing that changed. In this NPO, somehow these indices, this object will turn out to be completely equivalent to this object. Okay, because again, also here, so I said the rule here is I multiply this G with A, then this is A times G. But this was also exactly the rule to go from there to there. Okay, so you just reinterpret the whole thing in a different way and this turn this around, and this is also consistent fusion category, and this fusion category is this one. Wait, I only have 10 minutes left. Oei, very bad. Okay, so let's actually do something more interesting. Okay, let's actually do something in between. So you see here, I took the extreme case when I just take tensor products. Here I take the extreme case where my module is equal to vec of G. So, well, it feels very much like this should correspond to this classification of phases of matter in which I kind of look at all possible subgroups. Okay, so and indeed, it will turn out that this M, in general case, this M will be equal to G divided by H. Okay, so in this particular case, I took H equal to G. And in this particular case, I took H equal to 1. Okay, but what happens if I take an arbitrary subgroup? Then it will turn out that these labels, these MPO labels, these middle ones, will be kind of the coset labels. So there will be cosets. So the different cosets in your theory will be the labels of these dotted lines here in the middle. And you see, M itself is not, there's no multiplication. I cannot multiply a coset label with a coset label. That's not defined for a general group. But I can act with a group element on my coset label. So I will be able to act with C. So we'll have a C is vec of G. I will have an M is equal to the cosets. And it will turn out, and this is actually a non-trivial exercise, but it's not very complicated. As will turn out that this is the following. Will be the direct sum over G as an element of H, G, H. So it will be a double coset. Okay, so if I will explain what this is, times the representation theory of H intersection G, H, G minus 1. Okay, so this is very complicated, but it turns out that this is very easily derivable with these MPOs. Okay, so these will be the invariant subspaces that we will obtain when we just work with these. And what do we need for this? So here, in some sense, we worked with EREPs. Here we worked with regular representations. Well, here we just have to work with induced representations. Okay, so these are, we know that induced representations are also kind of, well, very well known. Okay, so basically an induced representation of a group G is something that you write down over A as an element of the coset of, and you act with G on A, and you look again, what is the coset label of this, times A, tensor D mu, and now this depends on G and on A. Okay, so induced representations are somehow a mixture about the regular representation, and so you take basically some EREP for H, and you take the regular representation for the cosets. That's how induced representations work. And you can now do exactly the same game as we played before. Okay, so basically you construct an MPO. You say, oh, let me kind of put my induced representation. So what my induced representation is now living here. And I'm doubling the indices of my induced representation of my cosets, just like I did this particular case. I doubled my indices. You construct using induced representations this MPO. You can see that this is indeed a very simple MPO algebra. You look for the invariant subspaces in this direction. And what you see is indeed, what will be the invariant subspaces? This is a group element A, and this is a coset label, let's say C1, and this is C2. Then, well, then this must be a coset label G times C1. This must be a coset label C times C2. That's exactly how this representation works. If I act with a symmetry on a coset, I have to act with my group element on my coset, and again take the coset label of that object. Okay, so what is invariant here? What you see, if this is C1 and C2, well, then what you need is that C1 minus 1 times C2 will be equal to somehow an element of G times GC1 times GC2 minus 1 times an H prime. So there will be an H and an H prime, such that C minus 1 C2 is equal to this thing times this thing. Okay, because again, this multiplication is only defined, you're working with induced representations. Okay, so you have to always say, this is defined up to an H. You put these things here, and what you see is that indeed, if C minus 1 C2 belongs to the same double coset as this thing, then, well, this cannot change. Okay, so the double coset label of these two things must be equal to the same thing. And that's why the invariant subspaces in this direction are completely labeled by these double cosets. So what is a double coset? It's basically if I have a group element G, I can multiply with any H1 and any H2. And the collection of this for a given group element G is the coset of G. And normally you have a left coset and a right coset, but here you have a double coset. And this is what emerges in a very natural way from this point of view. Is we get double cosets. You can construct this. You find the invariant subspaces, so it's a bit of work, but it's all very, at the end, linear algebra. And you see that indeed the invariant subspaces are exactly labeled by this object. Okay, so again, in this particular case, this is the bimodule. Okay, so we have like the bimodules. And this is almost all bimodules that you can construct given a sector C. Yes? If H is equal to G, this is this case. Okay? Because then there's only one coset and there's only one element. And if you want, if you do gauge theories, you're effectively working with H equal to 1. And then, because then M is equal to vec of G, and then these three things are equal to each other. And in this particular case, so what you see is already that these MPOs, that once you turn these MPOs in this direction, they are very non-trivial. They have very non-trivial fusion rules. The fusion rules are actually related to the fusion rules of this. These are the simple elements in your category or labeled by these double cosets. But how to figure out now how these MPOs multiply with each other, you get very non-trivial fusion rules. Of course, what you get is a different C. This is completely determined by C and M. And this is a Morita dual of C2. Yeah, so what is, so why you could say, oh, but why are you interested in all these things? And why is this so important to understand all this? Well, it turns out that all the possible ways in which you can break the symmetry of a quantum spin chain will be in one-to-one correspondence with finding all possible bimodules. Okay, so this whole question of classifying all possible phases of matter will turn out to be completely equivalent to finding all possible bimodules for a given group. Exactly. And this would only be part of it. It will turn out that you can construct more general MPOs that include the co-cycle, about the 2 cycle. Okay, and then you would have to have something like you have to put a psi here. But you can also put 3 cycles. And 3 cycles, but this is something that is, well, for this, actually this is what I want to do now, but I'm not so sure that I have time. You will have to change basically the rules. So this is, but it's still completely consistent. Okay, so 3 cycles will just be even other bimodules. Okay, but also 2 cycles come into play. This will be important for SPT phases in 1D. The 3 cycles will also kind of come into play. And this is actually very interesting. So, so maybe indeed this is a good moment to comment on this. So according to this C there will be, well, let's let me do this in the middle so that everybody can see it. But so we have this notion of a bimodule C, M, and D. It will turn out that there's lots of pentagon equations that will be satisfied. I wanted to do this now, but it seems I have no time anymore. But anyway, so there's some kind of lots of F symbols associated to this. Okay, so there's not just one type of F symbol. Turns out that there will be 5 F symbols associated to these things. Okay, so for example, these will be the Clebsch-Gordon coefficients. This will be the 6J symbols. These are the EREPs. Okay, this is the equivalent for category C and so forth. And in this particular case that I showed you here, we always took the 0 F symbols equal to 1. But now you could ask, what if I change this? This will also be consistent if I take here, let's say, a 3 cycle for my group. And if this is a non-trivial 3 cycle, then it turns out that you will not be able to construct MPOs. Okay, that only one of them will be allowed. You will only be able to construct actually this one. Okay, so if this omega, this 3 cycle associated, this solution of the pentagon equation of the C is a non-trivial 3 cycle, there's only one choice of M that is compatible with this, and that is exactly the anomaly. Okay, the anomaly will tell you that there's only one way of realizing this. Okay, there's no different ways. Okay, and turns out that this M, this I will see in the next lecture, so the number of labels in M will be in one-to-one correspondence with the number of ground states. Okay, so it will turn out that this M has a completely different meaning. If you look at quantum spin chains, there will be another M that is also like a module that will tell you what is the number of ground states in my system. And if I cannot choose this M equal to VEC, that means there is an anomaly, because there is no way that I can write down a system that has a unique ground state. It has either to be critical or symmetry breaking. And that's the anomaly. So anomalies completely fit in this language and have a very, very natural kind of meaning of it. But it seems I have to stop here. Yes?
For the case that Abhinav's asking with the non-trivial omega, shouldn't we have also multiple choices of M labeled by H's?
Yeah, sure. But okay, so it turns out that the possible choices of H, of M that are still allowed, you can still take the subgroups for which the three-co-cycle is trivial. For these ones, you can still do it. Indeed, it is a complete classification. So category people have solved these problems for ages. Okay, but let's say if you do the Z2 case, okay, there's only one non-trivial three-co-cycle, and then of course there's nothing. But I agree. No, of course there are sub cases. No? If you take a three-co-cycle that is not completely, there's only anomalous for a sub case or a sub coset or something like that, then indeed you can only gauge a subpart. But again, even there, you will not be able to choose M equal to VEC, and therefore there will still be an anomaly.
I'm also confused about your statement that the second case for which M was VEC G corresponded to gauging. I thought that M equal
No, I'm not gauging. I'm just saying these are the symmetries of a gauge theory. I'm not gauging at all. Gauging would be a duality transformation. Gauging will exactly be something that changes these symmetries. Okay, so this will turn out, so all duality transformations that you can imagine, and this is a complete generalization of Kramers-Wanier and Kennedy-Dazaki, all Jordan Wigner, all of these things fit in that framework actually, will be to change exactly from one representation to another one. Yes, this will turn out to be the complete picture in which you can classify all possible dualities. Will be exactly also the language of bimodules. It's I'm a bit cheating. It will turn out that you have the CMD. So as I saw, the Hilbert space is actually always defined by D. And dualities will be obtained by keeping D fixed, but taking another bimodule C prime and M prime. So a duality will actually change the symmetries. The C are the symmetries of the system. This D defines the Hilbert space on which you act. And to get a dual theory, what you will do is keep D fixed, but change the symmetry.
All of these are presentations of G-symmetric
Yes.
on different Hilbert spaces.
Exactly. So in that sense, it doesn't really fit this language completely. But okay, what I just to already project to what I want to do. If this is a bimodule and this is a bimodule, turns out that this is also a bimodule. Okay, and that means that now we have three different modules that are connected, and this will allow us to define new types of MPOs that will be the intertwiners for all your duality transformations that you are asking. So gauging will involve a triangle. Okay? Gauging will involve three different modules, and all possible ways in which you can connect them will give rise to all possible duality transformations. All of these will again be MPOs, but they will be MPOs that now map one Hilbert space to a different Hilbert space.
Frank, so this is all natural if you try to classify spin chains and the states of the spin chain.
Or string nets, or topological phases in 2D.
Right, but that's exactly what I'm trying to ask here. So in Julian's presentation, it's all about 2+1D, and it's about braiding structure and UMTCs that are classified by Drinfeld centers. In your case, the way it's presented, at least, it has been all about one-dimensional spin chains, and you construct MPOs. So what is the statement? You can understand all 2+1 dimensional topological theories by studying one-dimensional spin chains, or am I missing something?
No, what I'm doing here is trying to understand how I represent symmetries that are represented by fusion category. So I give you a fusion category and I say this is a symmetry. How do I represent these symmetries? That's the only thing I say. And these symmetries play a role in many different contexts. They can be the symmetries of quantum spin chains. They can be the symmetries of the entanglement degrees of freedom. So it's like a holographic point of view of TFT. So this will be, actually using this, we'll be able to construct all possible TFT. So all Turai Viro state sums will be directly constructed from somehow these MPOs. These MPOs will give you a direct way of constructing 2D non-chiral topological phases.
But for that, you have to extend to p-poles, right?
Sorry?
How do you pronounce that? Not
People.
people. Okay, so for this, you need to generalize it to people, right? If
Yes.
you want to do it with string nets. I see. But is there some sense of holography, like maybe what Apurva is going to talk next week, where if you know the states of the different MPOs for one-dimensional chains, you could think of it as a boundary of the corresponding.
Yeah, exactly. That's why, of course, the 1D and the 2D is very connected to each other. It will turn out, okay, what will be the string net? The string net will turn out to be something, you will need one of these F symbols. So where did I draw these? Turns out this 3F symbol will be somehow the object, will be somehow an object that looks like this. And it will be completely transparent to these MPOs. Okay? It will turn out that this MPO, so there's some degrees of freedom here. And it will turn out that this object is just satisfies some point. So this pink one is really the MPO. Okay, so this will be a wave function now. So I will make a 2D tensor network where on the virtual level, these are the degrees of freedom. And these red lines will be the symmetries of that thing. So these will be the topological lines. And these are effectively the symmetries that allow you to have anions in your theory. Okay, so these MPOs will be the Wilson loops in your theory. Okay, and of course, when you construct a big tensor network using these objects, you can look at the boundary of that object. And that boundary will, of course, inherit the symmetries of your bulk. And these are the spin chains. Okay, so the spin chains that we're talking about, spin chains with categorical symmetries, describe the edge modes in a TFT. And it will turn out that you can tune, if you have non-trivial symmetries and all this, that this is a very systematic way of understanding critical systems. It will turn out that indeed this TFT-CFT correspondence becomes extremely explicit in this context. Yes?
I have a question about Wigner theorem. So basically, Wigner came up with that symmetry should be represented unitarily, and now like we generalized it, and like in a sense that it can be like a unitary times projector.
Indeed, because I think that the key is that we are not really working on a tensor product Hilbert space anymore. Because there's these conditions, there's these kind of fusion rules.
But let's work on a tensor product. We can do that, right? We can.
Yeah, but then these are just unitaries, no?
No, but like.
So the tensor, if you have a tensor product space, that's actually only the case when M is equal to vec. That's the only case in which you have a tensor product structure. M must be equal to vec. Because right, then this looped, these dotted lines are not there. And then, of course, this is just here.
But like, for example, in this case, you can try to resolve your Gauss law, right? So
yes,
solve it and then write it in terms of H invariant degrees of freedom, and it will form a
yeah, sure. So of course, you can do that. No, and this is, of course, it's not an easy exercise given a certain spin chain to understand how can I even define what the Hilbert space is such that it has such a symmetry indeed. And in many ways, like an XXZ chain, you can phrase it for the non-trivial, non-invertible symmetry. To fit this in this framework is not so obvious. Okay, it's a non-trivial exercise.
Yeah, back to my question. So is it possible to show that? I think Apurva also asked that. But imagine you have a closed boundary conditions as you've been doing here. So and you have this MPO construction. So can we show that it's a unitary times a projector?
Yes.
So,
well, yeah, but there's more general solutions. But indeed, for unitary, if you use the unitary solutions, yes, sure, this is always a unitary times a projector. And if you take into account the boundary conditions.
Closed boundary.
No, but then it's not. You need to take into account all possible boundary conditions.
But imagine I have a system with a closed boundary. So I do not want to take all, I just chose to be closed. Okay, and I'm asking a question. So you say that it's a symmetry, right? Then I ask, like, is it a unitary times a projector? So,
yes, I think so. But the reason that I insist on getting all possible boundaries is that I need this to be able to implement this as a quantum circuit.
But like, what do you mean all boundary? Like, if I have a concrete system, then I have to fix the boundary conditions.
No, but of course, these boundary, so the boundary conditions, you add some extra degrees of freedom that play the role of the boundary conditions, and you can fix them as you want. Okay, so it doesn't affect at all your spin chain. Okay, so in practice, it of course, you're choosing a boundary condition is effectively fixing these extra degrees of freedom that play the role of the boundary conditions. But I will talk about this tomorrow. I will explain how to deal with this.
Let's thank Frank once more.